Our next speaker is Vincent with a talk about explicit cumulativity in CC omega.
Yeah, so hello. This is a joint work with Hugo Herbelin and Pierre Letouze, who are advisors my PhD thesis. So here's a brief plan of what I will talk about. In CC omega and pretty much several theories where there is a hierarchy of type universes, and there is a cumulativity. So there is a subtyping between them. I will talk about that, and then about how to make it explicit using coercions in order to achieve several goals that the fuzziness of an implicit subtyping hide and make more difficult than if there was an explicit version. So first, cumulativity, so a brief recap. In CIC or even in CC omega, which doesn't have the inductive types, I won't need for that talk. There is a hierarchy of universes, So there is the propositional universe separated of the type universes, unlike in other type theories, and there is this implicit subtyping between them. So prop is in type 1, there is also maybe a type 0 in coq or something, or a set, but I won't need it in this talk either. And each type is included in the following one, in addition of being inhabitant of it. And there is this subsumption rule that says that any inhabitant of a type also inhabits the supertype. So that's why it's implicit. And that's the source of the problems. So first, why we have it? It formalizes an intuition, pretty much logical intuition we have from set theory that there is this cumulative hierarchy of bigger and bigger universes of types forming the global universe. And it's useful for defining more or less polymorphically functions and type families over many universes, because if you do this on a bigger universe, you have it for all the lower ones. Also for axioms, talking about equality of proof terms requires equality type also on prop, and for also multiple rules differing only by a substitution of prop for type. Here another axiom where you have the universe appearing. And the disadvantages I already started to talk about are the non-uniqueness of type of term, trivially, and even up to conversion in a given context. And also there is this obstacle for extraction of programs. So in coq, there is this process developed by Pierre Letouze that allows to extract already automatically certified programs from from actual terms that have the specification that the type prescribes. And this process eliminates any subterm that's there only to certify that a sub-program does what we want it to do. And it does that pretty roughly currently. And if we can more fine-grainedly find what comes from prop in type due to the cumulativity prop included in type, it will be more practical to extract only the subterms coming actually from prop and keep the structure of the term. For instance, if it's a function, in order to still apply it in the extraction program. So an example for this link with the extraction I already talked about. If I have this function that has this type here argument, and then two function types with this x appearing, if I apply it on true, in coq it will work since E is the inhabitant of true, it's a coqism, and true is in prop, but prop included in type allows to apply it like that, and it will work, and reduce to 1, I guess. But when we do the extraction, we have this whole subterm that's in nat row true, which is in prop by impredicativity, since true is, and the extraction will replace the entire subterm then with an important value of the target programming language. So not respecting the function structure. So to remedy this, coercions. Coercions appear in many frameworks. Here it will be a coercion from the subtype to the supertype. And we don't want it to be an implicit coercive subtyping, because we could still have stuff like, maybe there is a tool just to write that because it's not written here. We could have this and say like f of, and we could have f from B to C, and we could have f of QE A, B, T convertible to f of A, or even without the f. But there are several subtyping that do that, especially Luo subtyping in his papers. So that's coercive, but still implicit in this way. We want to make coercions ineradicable in that sense. I don't know if that word exists in English, but even in French. But that means what that means. We don't want them to disappear. Yeah. No, it's a T. Thank you. I did it variables in minds. Okay, so that's it. And but we don't want to keep always A and B. We want to keep only the relevant information, so the universe we come from and the universe we go into, and the propagation of this information to typeformers. And we will also explicit not only prop into type, but also type I into type I plus 1, or in type J for higher J, because we want because of technical arguments, actually, and also because we want to use that, I will talk about it later, maybe to understand better the whole hierarchy of types in a type theory that has it. So our system is CC omega sub. Its syntax is like this. So the key ID is using subtyping marks that will go here in the coercions, and also in the subtyping symbol. We'll see that in the subtyping rules. So anything is pretty standard. There is this mark grammar here. We have arrow marks to account for the propagation of subtyping into the pi typeformer, the only one we have for now. And then we have this composition of marks that builds in the transitivity of subtyping for also technical reasons that we'll see next. Another feature of our system is that we keep the sort information here in domains, in type declarations, in contexts, and also in judgments. In the terms, it's because of reduction reasons that we want to remain, to keep subject reduction, obviously. So we need this information, not to lose it. And it will allow also unicity of sorting and of typing them. And yeah, and that's it. It's a bit heavy, but it works. Okay, so the marks more explicitly, more detailedly. We have it that expresses only the part that remains implicit in the subtyping, and since we explicit the whole hierarchy, it's only the reflexive part. So any type and universe is it's subtyped to itself. The double up is the subtyping of any universe S into the bigger one S prime, And we propagate, that's a difference with Asaf's work, for instance, on universe subtyping. We propagate the subtyping between types to their inhabitants. So this little up will be the under coercion from one type into its co-weight double up version. You'll see that then. And this is the retraction of the co-weight simple up that gets back into the lower universe or lower type coming from a double up quest one. And we have also the two subtyping mark formers, so between pi types. We propagate the subtyping covariantly, on codomains, obviously, and also contravariantly on domains, which isn't always done and which could allow us to also study more precisely what can or cannot be done by eta expansion in Coq. And then I talked about it already, this composition of marks that is necessary in particular to handle coerced universe into bigger ones. Now the rules, so I put all the subtyping rules. There's this reflexive one, this one of S in a bigger S prime. This square subset is for the usual order of universes, the meta order. Here it didn't compile it, it's a simple up for this one, so of A in coerced double up B if they are convertible. Same in the other way around. The propagation covariant in codomains and contravariant in domains is here, and there is the mark here. Here it shouldn't be the same sort. I don't know why it is, because there is no reason for it to be the same. This is only a side condition for variables that disappear with the brain indices. It's not important. But here it's important to coerce the variable that's into B for well-typing reasons. Here it's the built-in transitivity with the composition marks. And here it's just to expand to less reduced types while going down into the derivations. Here it's the congruence to coercions with the same marks. We don't have the trivial marks, I could call them, here, because that will make unnecessary derivation alternatives to the ones that already come from reduction. You see the reduction then, but that's it. And here, those are I call them the 8 rules, because the eta is reversed. It's the version of the restricted eta that we have in Coq for the coerced functions. And again, it will be more perhaps understandable with the reduction rules that follow. But if you have something applied here, we want it to be convertible to the function to be convertible to the function itself without applications, thanks to these rules. Okay, so the reduction rules. So the beta reduction is weak head. It goes also under coercions. Here it's the reduction from a trivial mark, so the coercion is just erased. This isn't well typed, but for technical reason it's still here. Maybe it will disappear. Here the composition just decomposes. And then when coercions are decomposed, we can compose then. Yeah, it's maybe unnatural, but that works better this way for subject to reduction reasons and stuff like that. So here we have the composition from S to S prime, and then from S prime to S second. That's just going from S to S second. There is the same with simple arrows in both ways, in both senses. And then with simple arrows in one sense, and yeah, simple arrows up, simple arrows, and down simple arrows. Sorry. If we compose, we have. Okay, thank you. We'll have also rules. Here it's the rule to decompose the arrow marks, and here are the equations that we get with the other rules that are oriented almost only to keep confluence and subtract reduction and so on. But what we want actually is those conversions that mean, to parse them, that mean that decorations of pi types, either exterior or of lambda, either exterior ones or insider ones, decorate them into the same thing up to convertibility. So that's it. Here the little pi is just the sort where the pi type goes and the sort where it comes from. And the key typing rule, so it's this, what becomes the subsumption rule. It becomes so the introduction of the question, of course. And what it makes on the example, so here true was in prop, it goes in type 1, for instance. And in parallel to that, the inhabitant of true goes in this coerced type with the simple arrow, corresponding simple arrow. And now the extraction process can only eliminate this subterm and keep the function structure. The results, I will go quickly. There are several commutation lemmas and usual lemmas, such as well sorting of the sort of a term, and commutation with conversion, subtyping, and substitution. That's usual. So we have the unicity of typing I already talked about, thanks to this explicitation. A type has only one, a term has only one type, sorry, in a well-formed context. We have several lifting lemmas. So if there is a reduction in the, this double bar is just erasing the questions, more or less. If you have in the actual current coq, let's say a reduction, you have it in with the decorations. If you have a conversion, you have it with decorations. If you have a subtyping, currently with cumulativity, in between the implicit versions, you already have it in the explicit version. And for the typing, lifting, we need an algorithm to, I will be very quick on that even if it's complicated, an algorithm, to decorate the terms and the type that you have in the implicit version with corrections well placed. So there is this algorithm. The non-trivial cases are for pi and for lambda and for lambda extraction and application. And so we have this huge number of very long side condition using the recursive calls and depending on what the result reduces to. Okay, and for application, you can, maybe I didn't include it or it didn't compile. We need to use also an algorithm to synthesize marks, subtyping marks between two given types. So here it is, for instance, the case of arrow marks between pi types coerced or not, because there are coerced pi types that don't reduce to pi types. So that's it. For sorts or coerced sorts, it is here, and you can see here the compositions that are a reason why compositions are necessary, because you have these marks that can be reduced to uncomposed marks or atomic marks and are required. And here is the theorem we hope to finish to prove that lifts typing from the implicit version. Here is the main one, that's for context, and that's for types. Here is the main one for terms. So if you have a typing here by a well-typed type, you need to have here you want to have here the well typing of its decorated version by the algorithm. And there is work to be done, but maybe we'll talk about it in the questions. That's all for me. Sorry for the time.
If I remember correctly, in the paper by Ali Asaf, he has kind of problems with his reduction system because of the subtyping of prop into type that is like causing him conference problems.
Yeah.
So he orients kind of coercion the way kind of going outside of the term rather than propagating inside, which to me has always been something a little bit strange. And I wondered if you have like a similar thing happening, or if you found a way to kind of avoid that problem.
Yeah, so I didn't put them. I put only the equations because of several reasons. One of them is that it always went too far on the right. Sorry, too far on the right of the slides. So yeah, we circumvent this because we have a way to orient this while making the equations enter the pi types and the lambda terms. In this way, for instance, here you see this entering this.
Yeah.
This rule is more or less this one, but not exactly, because here we can't do that. You see, this pi is the same for many different arguments.
Mm-hmm.
It's the sort where the pi types goes. So we can't reduce this.
Okay, so you managed to orient everything from left to right while keeping a confluent system.
Yeah.
Okay, nice.
Yeah, we manage, and we have also rules that erase coercions when they're already inside. We have rules like that. Yes, we manage, and for that it's crucial to have the sort here. So.
Okay, that's the thing that maybe Ali
that
doesn't
may
have.
be
Okay.
That was necessary.
Okay, thank you.
More questions?
I'm not sure if it's really a question, it's more like a remark or something.
Yeah.
The coercions you have are a lot like Agda-style cumulativity, which is you don't have cumulativity, you have lift, and then which creates a new type, and that has a constructor and an eliminator, which are the single arrow coercions in a way.
Yeah.
And this creates problems if you're doing hot, because you can equate stuff, but then it becomes isomorphic again when it's at a different level, because the thing is an explicit isomorphism.
Okay.
And I think you're fixing that actually because you commute through pi types. So I think that's interesting, but I'm not sure what it would be interesting to consider this in the context of homotopy type theory, where you have univalence.
So we didn't talk about the Agda features, but maybe that's what make it work here, yeah. Because we don't have the isomorphisms that you talked about here. Otherwise, that would amount to erasing maybe the questions. And about hot, we are in the long term hoping to use that better comparison, understanding, of prop into type, especially in order to maybe interpret it into hot, into the hash prop of hot with proportional positional resizing or things like that. I'm not sure if that's exactly matching your concern about hot, but
It's just in hot, if you have isomorphic types, you can make them equal.
Oh, yeah,
but then if they live at different levels, they become non-equal again, and that's sometimes an issue.
But here, so we not in hot, but I'm pretty sure we don't have the isomorphism, otherwise that would collapse what we want to separate. I'm sure maybe we will talk about it later, but yeah, no. Well, maybe that's it, but yeah.
Just to make sure, there is a plan to integrate something like that into COC at some point?
Yes, there is the plan to elaborate COC and its extraction process with this when it's...
And then would the user need to put in the extra coercions, or would that be inferred by the system somehow?
The user, you mean? The user would have to put them, or...
Yes,
or would
that's my question. Yeah.
I don't know. I guess some inference would be necessary and welcome. I'm sure. I guess I'm not sure, but the aim is that the algorithm would infer most of the things for us.
Okay.
But I'm not sure that if the user would need to do something at the beginning or something like that. The aim is that we have nothing to do in the algorithm do it for us.
Okay, perfect. Then thanks again.
Thank you.